Hey everyone, I hope you're doing well today. In this video, let's simplify n behaviors of polynomials. In all 10 of these examples that you see on the screen, all of these polynomials are going to be factorable. Feel free to pause the video whenever you need to stop and think, and also you can grab some paper and something to write with, but either way, let's go ahead and do some math together. For number 1, we have f of x is equal to x squared minus 3x minus 28. So the first thing we're going to do here is try to factor this. So we know it's going to factor into two binomials, and they're both going to start with x to get x squared. One of them is going to have a minus 7, and the other one's going to have a plus 4. To find the x-intercepts for this function, let's set f of x equal to 0. To make this equation true, in this binomial, x would have to equal positive 7, and in the binomial to the right, x would have to equal negative 4. Looking at this on a graph, we can plot our x-intercept of 7, 0 over here to the right, and our other x-intercept of negative 4, 0 over here to the left. Because the leading coefficient of the polynomial is positive, we know this parabola opens upwards. For the end behavior for this function, we can say that as x is moving towards negative infinity, or it's moving to the left forever, we can say that the function, or the y values, are going to be moving up towards positive infinity. And we can also say that as x is moving towards positive infinity, or to the right forever, we can say that the y values, or f of x, is also moving upwards in that positive infinity direction. For number 2, we have f of x is equal to negative 2x squared plus 3x plus 35. To begin, I'm going to go ahead and factor out a negative from this trinomial, so we have negative on the outside, and then we have a positive 2x squared minus 3x minus 35. Everything just flips signs on the inside. Once we do that, it's going to be a little bit easier to factor this, just because we have positive coefficients a little bit more. So we have this 2x and x at the beginning of each of these. That multiplies to get 2x squared. And now we just need two factors that multiply to get negative 35. Well, we need one positive and one negative. I'm thinking of putting a minus 5 over here to the right and putting a positive 7 over here in the left binomial. The reason why this will work is because this 2x times minus 5 is going to be negative 10x, and 7 times x is positive 7x, and those are going to combine to get the negative 3x in the middle that we see up here. Setting f of x or y equal to 0, we can go ahead and find our x-intercepts now. Setting this binomial equal to 0, you'll find that x equals negative 3.5. And setting this binomial to the right equal to 0, we'll find that x equals 5 would be the other x-intercept. Putting this on a coordinate plane, 5, 0 is going to be located right over here, and this negative 3.5, 0 is going to be located to the left. Because we have a negative leading coefficient for this function, we know this parabola has to be opening down. In terms of end behavior for this polynomial, as x approaches negative infinity, or as we go to the left forever, f of x, or the y values, are going to be going towards negative infinity, or going down. And as we move towards the right, or as x approaches positive infinity, f of x, or all the y values here, are also going down or towards negative infinity. For number 3, we have f of x is equal to 3x squared minus 10x plus 8. So let's go ahead and start by setting up our two binomials for this quadratic. We know we're going to have 3x and 1x as the leading terms in each of those binomials. And we need two negative numbers because 10 is negative and 8 is positive. So I'm thinking here of putting a minus 2 and a minus 4 over here. The reason that makes sense is because 3x times negative 2 is going to be negative 6x, and negative 4 times x is going to be negative 4x. Combining those, we're going to get this negative 10x that we see up here. Setting f of x or y equal to 0, we can now go ahead and see what our x-intercepts are. Looking over here and setting this equal to 0, x would have to equal 4/3 for this x-intercept, and looking for this other binomial, x would have to equal positive 2. Putting this on a coordinate plane, 4/3 is right around here, and 2 is just about here. Because our leading coefficient is positive, we can graph a function that looks something like this. For our end behavior, we can say that as x approaches negative infinity, or as the function moves to the left, f of x, or all the y values, are going to approach positive infinity or move upwards, and as x approaches positive infinity, or as the function moves to the right, f of x is going to go towards positive infinity as well. For number 4, we have this function f of x is equal to x cubed plus 125. It'll be helpful to know that when you have this pattern of something cubed added on to something else cubed, you can always factor this in a specific way of the quantity of a plus b multiplied by the quantity of a squared minus ab plus b squared. In this particular example, a would then be represented by this x that we have, and b will be represented by 5 because that's the cube root of 125. So going ahead and factoring this, we'll have this x plus 5 in the first set of parentheses, and in the second part, we're going to have a squared or x squared minus ab or minus 5x plus b squared or plus 25. So now going ahead and looking for the x-intercepts, we can say that for this binomial, if x was equal to -5, that would make this whole right side equal 0, so that's going to be one of them. And for this right side, because this was cubic, this part is quadratic, so we have to see where these two intercepts may be. Inside this parentheses, you're going to see that this is a quadratic, but this part isn't factorable. To know that for sure, you can go ahead and use the discriminant, or b squared minus 4ac, and if this value is positive, you would have two real solutions. If it was equal to 0, you'd have one real solution, and if it was negative, you'd have two imaginary or complex solutions. In this case, b is equal to -5, so we have -5 squared minus 4 times 1 times 25, and -5 squared is going to be 25, and this 4 times 1 times 25 is going to be 100, so we would get -75 for the discriminant. This confirms that we wouldn't have any real solutions or real x-intercepts on this part of the function. That being said, we can plot our x-intercept of -5 over here to the left. And in terms of graphing this polynomial, since it's a cubic and it has a positive leading coefficient, we know it's going to move up from the left side, and it's going to continue moving up to the right side. While cubic functions could have 3 x-intercepts, this one just has 1 because the other 2 are imaginary. For the end behavior for this function, we can say that as x approaches -infinity, or as we go to the left, f of x is going to be approaching -infinity as well. It's going down on the left side. And we could say that as x is approaching positive infinity, or as the function is moving to the right, we can say that f of x, or all the y values, are approaching positive infinity, since it's going up to the right side. For number 5, we have f of x is equal to x squared minus 10x plus 25. And for this one, this is a perfect square trinomial, but I'll just go ahead and write out both binomials here. And so we have x and x, that's kind of nice here, and we need two negative numbers. I'm going to go with -5 and -5. So you're going to notice that these two binomials are actually identical, so that's why I said it was a perfect square trinomial. And so we can write this as the quantity of x minus 5 squared. To find the x-intercepts, we can set y equal to 0, or f of x equal to 0, and we're actually just going to have one x-intercept, but it has a multiplicity of 2, or it happens twice, so I'll show you what's going to happen in just a moment. We have x equals 5 for our x-intercept. Here's our x-intercept of x equals 5, and roughly our parabola would look something like this. Whenever a polynomial has an x-intercept that has an even multiplicity, like in this case x minus 5 happens 2 times, the function's not actually going to cross the x-intercept at that location, rather it's going to bounce and stay on that side of the x-axis. For the end behavior of this function, as x approaches -infinity, or as the function moves to the left, f of x, or the y values, are approaching positive infinity because it's going up, and as x is approaching positive infinity, or it's going to the right, f of x, or the y values, are also going to positive infinity or moving upwards. For number 6, we have f of x is equal to x cubed minus x squared plus 2x minus 2. Whenever you have a cubic polynomial that has 4 terms, I strongly recommend trying to factor by grouping. So what I mean by that is you would then try to group the first 2 terms, or this x cubed minus x squared, in one set of parentheses. And after it, we're going to then group the next 2. So we're going to see if we can group this and say that we're going to have this 2x minus 2 in the second group of parentheses. Once we do that, we go ahead and factor out the GCF of each of these binomials. So we're going to have this x squared for this first one on the outside, multiplied by x minus 1 on the inside. And for the second binomial, we're going to factor out a 2 here. And let's see what we're going to have on the inside. We really should have an x minus 1 left over on the inside of this binomial. Looking at this term and this term, notice how both of them have x minus 1. So we're going to go ahead and factor those out from both of them. So let's see, on this left side, we're going to have x minus 1 since they both had that in common. And what was left over is going to be the x squared plus 2. Setting f of x, or y, equal to 0, we can then go ahead and find out the x-intercepts. From looking at this binomial, we know that x equals 1 will be one of our intercepts. But for this other one, this is a quadratic, and we need to check that out and see if we can figure that out. So we have x squared plus 2. When is that equal to 0? Well, if you take away 2 from both sides, x squared would have to equal -2. And if we took the square root from both sides, x would have to be equal to the square root of -2. and that's going to be imaginary or complex. So we're not going to have any x-intercepts that are real for those parts. Going ahead and plotting the one x-intercept we know of x equals 1 right along the x-axis there, we know it's only going to have one of those intercepts, so we're going to have some sort of cubic function that looks something like this, give or take. For the end behavior, we can say that as x is approaching negative infinity, or as the function moves to the left, f of x is approaching negative infinity, it's going down. And to the right side, as x is approaching positive infinity, we can say that f of x, or the y values, are going up forever, or towards positive infinity. For number 7, we have f of x is equal to negative 2x cubed plus 10x squared minus 4x plus 20. Since we have another cubic polynomial that has 4 terms like the last example, let's go ahead and factor by grouping. So in this first one, we'll group this negative 2x cubed plus this 10x squared. We're going to have this minus over here. And for the second grouping, let's put the 4x in the beginning, and let's write minus 20. We need to write subtracting 20 just because if we distribute the negative that's right in front, this negative right over here, it needs to distribute, so this would be negative 4x and this would be plus 20. So that's why we got to write minus 20 there. For this first grouping, let's go ahead and factor out the GCF, which is going to be negative 2x squared, and what would be left inside should be x minus 5, I believe. And for the second grouping, let's factor out a 4, and let's see what would be left over inside. I think it's going to be x and then minus 5. Seeing as how both of these terms have x minus 5, we can go ahead and factor that out as the GCF. So we're going to have x minus 5 out in front, and what would be left is going to be this negative 2x to the second power minus 4. Looking for x-intercepts now, looking at this first binomial, if x was equal to positive 5, then we would have an x-intercept located there. And for the second one, we have a quadratic, so we have to do a little bit more work. If we set that equal to 0 and add 4 to both sides, we would get negative 2x squared is equal to 4. Dividing both sides by negative 2, we would get x squared is equal to negative 2. And if we took the square root of both sides, x would equal the square root of negative 2, which means that we'd have 2 complex solutions there. So to graph this cubic polynomial that has a leading coefficient that's negative, we're going to get something that looks like this. This is just a rough sketch. Just make sure that it's going up to the left and down to the right, and that it only goes through the x-axis one time. For the end behavior here, we can say that as x approaches negative infinity, or as we go to the left, f of x is moving towards positive infinity, or it's going up, and towards the right, as x moves towards positive infinity, we can say that f of x, or the y values, are moving down or towards negative infinity. For number 8, we have f of x is equal to 3x to the 4th power minus 243. So to start this one, I think what I'm going to do is factor out a 3 first. I think that's going to be a GCF here. So left over, we're going to have x to the 4th power minus, I think that's going to be 81. I think that's right. For this pattern for factoring, you're going to want to remember your difference of squares, or a squared minus b squared, because whenever you have something that looks like that, you can then factor into the sum of those square roots multiplied by the difference of them. So a plus b times a minus b. So in this case, what I'm saying is I think a squared is going to be the x to the 4th power. So a would be the square root of that, or x squared. And b would be b squared would be 81. So b would be the square root of that, or that would equal 9. So going ahead and factoring that, I think we would have 3 times the quantity of this x squared plus 9. And then we have another group here of x squared minus 9. Now looking at this, there's no such thing as a sum of squares that we can factor nicely here, but we do have a difference of squares again over here, since x squared and 9 are another set of perfect squares, and there's a difference of them again. So let's go ahead and factor this further. We'll have 3 over here, and then we'll have x squared plus 9. This part was not factorable. You'll see it's going to be imaginary anyway. And this over here is going to factor into x plus 3 times the quantity of x minus 3. For this first grouping over here, the intercept is going to be imaginary. So if we set that equal to 0 and subtracted 9 from both sides, we would get x squared is equal to negative 9. And taking the square root from both sides, we would get x equals the square root of negative 9. And we know that's imaginary, so we don't really have to worry about that in terms of graphing. Over here, we would have x is equal to negative 3 as one of our x-intercepts. And then looking over at the third part, well, maybe I'll keep this the same color. This would be x equals positive 3. That would be another x-intercept. On a coordinate plane, we can go ahead and put this negative 3 over to the left and positive 3 over to the right. Those are going to be our only two x-intercepts that we can see on the real number line. And more or less, our function is going to look something like this. For our end behavior, we can say that as x approaches negative infinity, or as we go to the left, f of x is going to be approaching positive infinity. It's going up. And as x is going towards positive infinity, or as we're going to the right, f of x, or the y values, are also going towards positive infinity. For number 9, we have f of x is equal to x to the 5th power minus 4x to the 3rd power minus x squared plus 4. Going ahead and trying to factor by grouping, since we have 4 terms again, I know it's to the 5th power, but I'm still going to give it a try just because of that pattern. I'm going to group this x to the 5th power minus 4x to the 3rd power, and let's see what the other grouping is going to be. I guess we'll just keep these together, right, and have this be positive x to the 2nd power, but we have to write this minus 4 to keep things consistent. So if you distribute that negative, we should get the original polynomial. Factoring out the GCF for this first grouping, I think that's going to be x to the 3rd power. And if we factor that out, I think we're going to have x to the 2nd power minus 4. And for the second grouping, we can't really factor anything out, but I'm going to write minus 1 just to keep things consistent to show that there is something there. And on the inside, we're going to have this x squared minus 4. That's what we're going to have as the grouping, okay? So the reason why I wrote the minus 1 is because now when we factor out the x squared minus 4s, this is going to be easier to kind of see and understand, but we're going to have x cubed minus 1, right? Like those are the parts that they didn't have in common, and then what they did have in common was they had the x squared minus 4. So I'm going to go ahead and write that x squared minus 4 just like that. Now setting this whole thing equal to 0, we got to see if we can find some x-intercepts, but you're going to see that we're going to run into a little bit of an issue here. So looking at this part here, this pattern is going to be a difference of cubes. So pretty similar to sum of cubes, when we have difference of cubes, or a cubed minus b cubed, that's going to be equal to the quantity of a minus b times the quantity of a squared plus ab plus b squared. That being said, in this example, let's make a equal x, or the cube root of x cubed, and let's make b equal 1, or the cube root of 1. So going ahead and factoring that difference of cubes, we're going to have x minus 1 times the quantity of x squared minus x plus 1. In terms of this x squared minus 4 you see over here, hopefully that looks familiar as being the difference of squares, so that's going to factor into x plus 2 times the quantity of x minus 2. This one right over here is not going to be factorable, so we don't have to worry about it. But over here, from this x plus 2, we know we're going to have an x-intercept at x equals negative 2. And looking at this one, we're going to have another x-intercept at x equals positive 2. Putting this on a graph, we'll have one x-intercept here at x equals 1. Then we have the one at negative 2 over here to the left, and one at positive 2 over here to the right. If we're going to go ahead and graph this polynomial, it's going to look something like this. We have a positive leading coefficient, so on the left side it's going down. It's coming up, it's going to do some weird stuff because of the complex number. It's going to come down through, but then it's going to come back up through on the right side. For the end behavior here, as x is approaching negative infinity, then the function, or f of x, is going to be approaching negative infinity as well. And as x is approaching positive infinity, or as it's going to the right, f of x is following suit and also going towards positive infinity, but in the upwards direction. Here's the 10th and final function for this video. We have f of x is equal to 2x to the 4th power minus 58x squared plus 200. For this one, I'm going to start by factoring out the GCF, which is going to be 2, and factoring that out, we'll have x to the 4th power minus 29x squared plus 100. While the degree of this polynomial is a little higher, it still follows the same pattern as the trinomials we typically work with, so let's see if we can factor this. The square root of the x to the 4th power is going to be x squared, so we'll go ahead and put those in each of the binomials. 100 is positive, so we need two negatives since the 29 is negative, and I think I'm going to go ahead and put a minus 25 and minus 4 in each of these binomials. Now, taking a look at this x squared minus 25, hopefully that looks familiar as a difference of squares. We can go ahead and factor that as x plus 5 times x minus 5, and then taking a look at this x squared minus 4 to the right, that one's a very similar one as well, and that's going to be x plus 2 times a quantity of x minus 2. From this term right here, we know we're going to have an x-intercept at x equals negative 5. Over here, we'll have another x-intercept at x equals positive 5. Over here, we have an x-intercept of x equals negative 2. And our final x-intercept is going to be x equals positive 2. For intercepts, we have this negative 5. We have a positive 5 over here. And then we're going to have a negative 2 and a positive 2. Because this polynomial has an even degree and a positive leading coefficient, we know that the function is going to come through this first x-intercept, come through the next one, go through again, and through one more time through the last one. Since all of these had an odd multiplicity or just happened one time, the function always crosses through the x-axis at those locations. For the end behavior, we can say that as x approaches negative infinity, or as the function moves to the left, f of x is going to go up forever, or it's going to go towards positive infinity. And as x approaches positive infinity, or as the function moves to the right forever, f of x is saying that it's going to be going to positive infinity as well. And there you have 10 different examples of analyzing polynomials and their end behaviors through factoring. Hopefully going through each of these examples in detail helped you remember how to factor some different types of patterns, how to use the leading coefficients and the degrees of the polynomials to write the end behaviors of each of these functions. If you found this video helpful, feel free to give it a thumbs up, and as always, keep up the great work, and I'll see you in the next one.